Okay, hi everybody. I'm Dr. Becky. My presentation today is called Elderberry and the Cytokine Storm. Um, I wrote this talk in response to the internet rumors that were going around that elderberry syrup would kill you if you got COVID-19. Um, Most of this presentation is actually going to be a deep dive into the immune response and the details of how our immune system works in response to respiratory infections. And we'll talk about elderberry a little bit at the beginning and a little bit at the end. But to really understand how elderberry works and how it got caught up in this rumor, we really need to understand how the immune system works in detail and what a cytokine is in the first place. All right, so the short answer to will elderberry kill me is no. Elderberry syrup will not kill you, certainly not by itself and not even with COVID-19. And again, in order to understand that, we're going to need to talk about how the virus works, how the immune system works, what the heck cytokines are in the first place, and then once we understand cytokines, we can look at what a cytokine storm is. And then once we understand all that, the explanation of the elderberry stuff actually makes perfect sense, and it's really short, and we'll get back to that as our sort of grand finale at the end. Okay, so the first thing we need to do is do an overview of the immune system. And the first place we need to start is looking at what cells are in the immune system. I did not turn that on, so now we have a laser pointer. So we see two sets of cells here. They're all white blood cells. So when you get your blood drawn and you do a CBC and they look at the white blood cell count, it's taking into account all of these different kinds of white blood cells. Sometimes if you look below the white blood cell count, there'll be what's called a differential. And that's going to be telling you how many of each of these different types of cells there are. And as we're about to discover, there's a whole lot of subsets for some of these cells as well. One more thing that I want to talk about before we move off of this slide is you'll see that they're in two major groups. This group of cells on the left side of your screen are the white blood cells that are part of what's called the innate immune system. In particular, I want you to pay attention to the neutrophils, they're key players, and the monocytes, those are also key players. And it's important to know also that the monocytes become macrophages, and they also become one other kind of cell called a dendritic cell. And they do that when they're in the bloodstream, they're monocytes. When they migrate into the tissues to help fight infections, they become macrophages and dendritic cells. I'll go ahead and tell you right now that the macrophages and dendritic cells, one of their main jobs, well, their two main jobs are to take all the stuff that gets processed in the tissue after it's been fought and blown up and take all that tissue through the lymphatic system and to the lymph nodes where it's going to present pieces of the pathogens called antigens to the B cells, which are going to make antibodies to those pathogens. And along with those scraps of antigen, they're also going to bring chemical messengers called cytokines to the T cells. Now, in the lymph node, the T cells and the B cells, which are the two different main categories of the white blood cell type called lymphocyte, the T cells that are sitting in the lymph nodes are what's called naive T cells. They haven't differentiated yet into one of the many different kinds of T cells they can become. So those are the main things that I want to sort of point out here. Now we're going to look at sort of a family tree of the white blood cells, and this is going to give us a little bit more detail about all the different kinds of cells. So once again here we see, here's the immune system, meaning the white blood cells. And you'll notice that it's divided into an innate immune system and an adaptive immune system. The innate immune system could also be called the non-specific immune system. And the reason we call it this is that, number one, it's the first response of our body. The other reason it's called like the non-specific or innate immune system is that this group of cells, no matter what the problem is, all respond the same way. So if you get a bacterial infection in your tissues, or if you have an injury like a sprained ankle or a bruise, or you get a burn, or you get frostbite, or you get a viral infection, no matter what it is, the innate immune response is exactly the same. where we get into the adaptive immune system, where the adaptive immune system means that we're making a specific response to a specific event or pathogen or injury. So that's why we call it adaptive. So again, the thing that's going to take us from the initial innate immune response and carry that immune response over into the adaptive system are these dendritic cells, which are called antigen presenting cells. So they're going to take little bits of what they found during their innate response, and they're going to carry those little bits, which are called antigens, over into the lymph nodes, where they're going to present them to B cells and T cells. And the B cells will begin to make antibodies, and then the chemical message that comes along with that antigen is going to determine which of the different kinds of T cells those naive cells will turn into. Now, at any given time, we do have all of these different kinds of T cells working and doing things in our body. But when there's an infection and we get a really loud signal that it's a particular kind of infection, different ones of these cell lines will be activated in larger numbers, and then they're able to take more specific activity. So let's look at all these different kinds of T cells, because some of them are particularly important when it comes to viral infections. So particularly, we want to pay attention to the Th1 set of cells. These are the primary T cells that help fight against infections, in addition to the antibodies that are made by the B cells. The next set, I'm probably not going to mention it too many other times, but they are relevant to viral infections, are the Th17 cells. These cells are more aggressive, and they do more tissue damage as they're trying to get to the infection. These cells, it's not super relevant at the moment because we're talking more about viral infections, but it turns out that these Th17 cells are the cell line responsible for tissue damage when someone has an autoimmune disease. So that's what these guys do, and when we start talking about the cytokine storm, the Th17 cells become relevant. Also relevant, sort of specifically to the cytokine storm, are the Th22 cells. These cells, when they are present in large numbers, they actually make the antibodies made by the B cells more aggressive. So again, when it comes to the cytokine storm or to autoimmunity, these cells become particularly relevant. I'm going to skip Tregs for a second and bounce over here, and we're just going to take a quick look at these two cell lines, the cytotoxic T cells and the NK cells. Both of these cell lines have similar activity. They are cells capable of directly attacking and killing other whole cells. So that's helpful with bacteria because those are whole cells. These NK cells also kill cancer cells. This is our body's built-in anti-cancer network. And then they can also help kill viruses and bacteria directly. So these guys are super, super important in our immune response to infections. Now let's go back to these Tregs. So the Treg cells are the ones that are ramped up once the infection is cleared. The Tregs send the all clear signal to the rest of the immune system saying, mischief is managed, job is done, everybody can clean up and go home now, we don't need you anymore, right? It also tells the B cells, so when the B cells start their antigen production, whichever specific line of B cells has been selected by that antigen, they go into rapid replication, and we get gazillions of that particular B cell that makes that particular antibody. When the Tregs come online, they tell all of those B cells to self-destruct because we don't need all of that antibody and all of those cells anymore. And it tells the few remaining cells to become memory cells, so that should we see that pathogen again, we'll be ready to make an instant response and boot the antibody response right back up very quickly. That B cell antibody pathway is what gives us immunity to infections that we've seen before. All right. So I think that's a big overview. Oh, one other thing. innate immune system has its own deregulation or resolving process that uses a specific set of cytokines that tells the innate immune system that it can calm down and that mischief has been managed. All right, so we've looked at all of these. The next thing I want to do is dive into the innate immune response specifically, because that's where the inflammation in the tissues actually happens. In the case of respiratory infections, this is what triggers phlegm and fevers and aching and things like that. So we're going to take a closer look at that, and we're going to use this picture to do that. All right, so the first thing I want to do is give you a little orientation of the picture so you can see what these different compartments are. So this top compartment here, this is a blood vessel and a capillary that's going, feeding the tissue. This section here is the actual tissue in question. So if we're talking about respiratory infections, this is lung tissue. If we were talking about muscles, this would be muscle tissue, or the dermal tissue in your skin. It could be the epithelial tissue lining of your GI tract. So this is the actual tissue. And then this little tube down here, this is a lymphatic drainage vessel. So it's sort of like a blood vessel, only it's much flimsier. And lymphatics flow through here and take the waste products from the tissue and send them into the lymph nodes. So this is the transport system that transmits the information from the innate immune response, carries it through the lymph vessels to the lymph nodes where the lymphocytes, B cells and T cells, are waiting. All right, so now that we sort of have our orientation, there's one more little piece of information that I want to tell you before we start. So imagine that all of this is full of, for our sake, lung cells. In addition to the lung cells, there are going to be fibroblasts that help make up the structure of the tissue, but there are also going to be some monocytes that are just hanging around in the tissue as sentinel cells. So their job is to survey the chemical environment in the tissue and send out reports in the form of chemical messengers called cytokines. So it's supposed to listen to the cytokines around it and then send out cytokine reports to the tissue to let it know if everything's okay or if there's trouble. All right, so it's sort of like the watchman in the town saying 12 o'clock and all's well, 2 o'clock and all's well, or oh dear, Houston, we've got a problem, send in the Marines. All right, so that's what these sentinel monocytes do. All right, so I'm going to go through this illustration twice. Once I'm going to show you what the innate immune response looks like when everything goes to plan and we clear the pathogen and then the inflammation resolves. The second time I want to go through it and show you some places where things can maybe go wrong, and we can get into either a cycle where inflammation increases and increases and increases, eventually becoming a cytokine storm, or becomes a cycle of chronic inflammation that doesn't resolve, that happens with a lot of chronic diseases. So first let's look at how it's supposed to work when things are working right. So our sentinel monocytes are surveying around and they suddenly start picking up signals that there's been cell damage somewhere. They start to perceive that there are molecules around that should only exist inside of cells, like ATP or other intracellular debris. They sense those and they say, oh dear, that's bad. Houston, we've got a problem. Now they release certain specific cytokines. We're going to talk about which ones later, but they release cytokines into the surrounding tissue, calling out a distress signal and saying, we need help. So that distress signal floats through the tissue and it eventually gets to the lining of that blood vessel that we talked about here at the top. When that distress signal hits the blood vessel, these little fingers sprout up out of the cells that are lining the blood vessel, and those are called adhesion molecules. And those adhesion molecules are very specific for just one kind of white blood cell, and that's the neutrophils. These guys right here. All right? So those adhesion molecules start sprouting up, and what they do is they start attracting the neutrophils, and the neutrophils start slowing down in the bloodstream. And then they start rolling along the edge of the blood vessel, and eventually they come to a stop, and then they fall through a gap between two of the cells that make up the wall of the blood vessel. And that's how they enter the tissue. Now, the neutrophil's job is to then follow that signal and migrate to where there are bacteria, or maybe there was a really bad, like you twisted your ankle and have a bad sprain or a broken leg or a bruise or a burn, and there's fragments of cells that have been damaged. So any of those, whatever set off the signal, those neutrophils are going to migrate to that area, and they're going to start munching up the broken cells or the debris or the bacteria. Now, when they migrate in and start their Pac-Man process, two things happen. One, they send out another signal that floats up to the blood vessel and starts to call in another kind of white blood cell. The other thing that happens, and this is very important, is that a self-destruct timer starts. And that self-destruct timer lasts somewhere between 6 and 10 hours. And so they send out a signal that says, hey, we've done our job, we're ready to be airlifted out, come and get us. And so that signal comes up, and you get a new set of adhesion molecules that pops up on the blood vessel wall. And those new adhesion molecules are specific for monocytes. And so that then slows the monocytes down. They start rolling along, get slower and slower. They find a gap, stop, and fall through into the tissue. Now, what was a monocyte in the blood, as it translates into the tissue, it changes form and becomes this gigantic amoeba-like cell called a macrophage. And then a few of them also become dendritic cells. So now that monocyte is a macrophage, these macrophages in this picture are very boring looking. They're really actually these big wavy amoeba things. So those then go and find those neutrophils who have sent out basically an eat me signal. But it basically says, come get me, come pick me up, I've done my job. And my self-destruct timer is on, so you better come get me before I blow up. So the macrophages then engulf the neutrophils, one each, and when it engulfs the neutrophil, it becomes what's called a Reiter cell. You don't really need to know that, but since it's on the slide, I thought I'd say the word. Anyway, once it engulfs that and becomes a Reiter cell, it sends out a third message that says mischief managed. It says, we're good, we don't, this neutrophil's been cleared, we don't need another monocyte. All right, so assuming there's enough macrophages to capture all of the neutrophils that have captured all of the debris, then that final signal is the main signal, and we get resolution of inflammation. The Reiter cells then carry those neutrophils into the lymphatic system. The neutrophil, once it's been engulfed, instead of exploding in an organized manner, it disintegrates, and then the macrophage and the dendritic cells sort through all of the debris, and they find little scraps that are unique, that are antigens that they can present to the T cells and B cells when it gets to the lymph node. Okay, so that's what that system looks like when everything's going right. There's another option though, and that is that things cannot quite go right. So let's say we have a really big infection. Huge numbers of bacteria have gotten into the tissue. That sends out a really big signal. We get a whole bunch of neutrophils coming into the system. They eat as many of the bacteria as they can, but they can't clear all of them. So that come into the call for more neutrophils keeps going. All right, and so we get more and more and more neutrophils, and then they send out the signal for monocytes, but there's often not as many monocytes as there are neutrophils in the system. So if there's a really, really big call, we might not end up getting enough monocytes that turn into macrophages to clear all of the neutrophils. Now here's where the next thing could go wrong. If some of these neutrophils aren't eaten by macrophages before their timer goes off, they'll actually explode. And then not only do you have the initial infection or the initial injury and damage problem and all that debris. But now you've got all the debris that's inside the neutrophil. So the original debris it ate, plus all the innards of the neutrophil, plus all the really caustic, intense enzymes that neutrophil was using to dissolve and break down the bacteria or the other cells. So now that splashes on all these other cells and starts to damage those. So now you've got exponentially more damage in the tissue that makes an even bigger come and get me, eat me signal, which then tries to continue to call monocytes. But if there weren't enough to clean up the original thing, there's even less chance of there being enough to clean up these new neutrophil, the damage that the neutrophils have done on top of that. So that's how we can get into either a forward cascading, increasing inflammation cycle, or can get into a loop of chronic inflammation. All right. The rest of the system, whether those pieces go right or not, the Reiter cells that do make it out do go into the lymph nodes, they go into the lymph vessels, then to the lymph nodes, present their antigens to T and B cells. So all that part goes the same. And those Reiter cells do still send out a resolution signal, but it's not as loud as the continued signal that there's lots of damage happening. All right, so let's look at that in a little bit briefer summary in a kind of different graphic. So this is when it works right. We've got infection or damaged cell. That sends out the call. It calls for neutrophils. The neutrophils come into the tissue and they eat and destroy whatever the problem is. That starts their self-destruct timer and also gets them, they start calling macrophages. The macrophages come in, they eat the neutrophils, they send out a resolution signal, and the mischief is managed and the infection is cleared and the inflammation is resolved. So that's the good version, and that's what happens truly most of the time. This is resolution failing. So we get our same infection, we get the same call for neutrophils, the neutrophils come and eat and destroy, their self-destruct timer starts, but there aren't enough macrophages that come into the tissue. So we get too few macs, not all the neutrophils get cleared, and then some of them are left to blow up, and then you get even more cellular debris damage that needs to be cleaned up. So we have a bigger inflammatory damage problem than what we started with, and so then the cycle continues. So how do we ever get out of that cycle? I've had people ask me that. And so if it's an infection, this cycle will ramp up and up and up until the infection's finally cleared. And once there's no more infection to clear up, then we'll stop getting as much. That'll lower the signal to call in neutrophils. So instead of 100 neutrophils called in, then once the infection's cleared, you do still have to clean up the debris from the other neutrophils blowing up. But instead of calling in 100, it might call in 50. And then that clears a little bit more. And then we might have to call in 20, and that clears a little bit more. And slowly that infiltration signal goes down and the resolution signal goes up. And eventually we get resolution. So that's how it does self-resolve eventually. When people have autoimmune disorders or arthritis or other chronic inflammatory situations, this doesn't so much grow and grow and grow, but it stays in an unfulfilled loop where it just never quite gets that full resolution. Okay, so now that we know what the process of the innate immune system is, let's dig in a little bit more and look at cytokines. So cytokines, as you've guessed and surmised by now, are chemical messenger molecules. These are chemical messengers that are made by and listened to, received by all the different kinds of white blood cells, and in fact other cells as well. There's more than 100 different cytokines. So think of them as like words in a language, or letters used to make words, or letters used to make logos or slogans. The messages tend to be pretty simple, upregulate this, downregulate this. And each one has a different message, but when the same cytokine binds to two different kinds of white blood cells, that same cytokine might tell those two different white blood cells to do something different. All right. So think of this as there's 100 people in a room at a big party, and initially they're all just having conversations and responding to each other because we've got sort of this homeostasis thing going and nothing major is happening. And then somebody says fire, and then that message spreads and everybody takes particular action. All right, so that's what the cytokine messaging system is sort of like. It's not linear in any way. It's this web-like conversation of all these different cells sending all these different messages to each other all the time. So it's complex. And it's important to remember that when we talk about, especially when we get to the cytokine storm and why elderberry is not a problem, thinking that we can't think of these cytokine message systems as straight lines, nor can we think about them as being the only message that's being sent. There are always multiple messages being sent. There are always resolution messages pushing back against the inflammatory messages. All right, did we talk about all of those? Yes, we talked about all of those. All right, so as you saw when we talked about the innate immune system, some cytokines signals bring the macrophages in, some bring neutrophils in, some call for the creation of antibodies. One other thing when we're talking about antibodies, remember I said it sorts through and looks for specific scraps that are unique. One of the other things those dendritic and macrophage cells do when they're sorting through is they're sorting self from foreign invader. And so when they bring those antigens to the lymph nodes, it's really important that those antigens are also presented with a cytokine message that says, pay attention, this is a foreign invader, we need to kill it, versus this is just a piece of us, just ignore it, we're just taking out the trash. All right, so it's really important that the B cells get those different messages. Otherwise, they can start making antibodies to our own tissue, and that is one of the ways that autoimmune disease gets started. Some cytokines signal naive T cells being turned into NK cells or cytotoxic T cells. And then there are also the cytokine messages that are resolvins in the innate immune system and are also the one cytokine signals that turn up the production of T regulatory cells, which tell all the other kinds of T and B cells to chill out and calm down because mischief has been managed, right? Okay. So now that we sort of have a feel for what cytokines are, and we understand that there's an innate immune response where our inflammation happens and how that transfers crucial data to the adaptive immune system, and it can take more specific action with various T cells and antibody producing B cells. Now that we understand all that, and that the thing that's sending all those messages are cytokines, and that there's hundreds of cytokines sending different messages, and that the balance between those messages is what determines if our immune system becomes more active or less active, and specifically what activity the immune system is doing, right? So now that we understand that, we're going to talk about 8 celebrity cytokines. So these cytokines are very powerful, and they're the initiators of either the immune and inflammatory response, as this set is, or the resolving immune calming response. So when we're talking about cytokine storms, we're talking about the 4 cytokines that initiate the immune response or the inflammatory response, growing and growing and growing and growing, and that message getting louder and louder and louder and louder, and eventually it hits a threshold beyond which there's no hope of the resolution signal ever catching up with it. And then we cascade forward faster and faster and faster, getting more and more and more tissue and cell destruction to the point where it becomes fatal. So really nasty things like Ebola or hemorrhagic fevers, this is how they kill people. This is also how COVID-19, the people that become very, very ill from it, it is a cytokine storm that kills them. And the cytokine storm plus what the cytokine storm causes to happen in the lungs that kills people with COVID-19. So our 4 celebrity cytokines are interleukin-1 beta, tumor necrosis factor alpha, usually just referred to as TNF alpha, interleukin 6, and interleukin 8. So these four are the ones that are sent out by the sentinel monocytes that say, Houston, we have a problem, send in the neutrophils. These also go over to the adaptive immune system and tell the adaptive immune system to ramp up production of Th1 cells, Th17 cells, T8, and possibly Th22 cells. The TNF alpha in particular activates the Th22 cells. The tumor necrosis factor and the interleukin beta and the interleukin 6 all activate the Th17 cells. All four of them activate the Th1 cells. So those four cytokines are essentially our call to kill and keep killing molecules. All right. Now our famous resolving cytokines. The first one is called resolvin. That is the cytokine that is sent out by the neutrophils after they've eaten the stuff in the tissue. That is the eat me signal. So the resolvin calls for monocytes to come in and become macrophages and eat the neutrophils. Other resolution molecules are prostaglandin, TGF beta or transforming growth factor, and interleukin 10. Now there's many more, both call to kills and resolving, but these are the four main ones that start the processes. So our mischief managed signal, I just like that. All right, so now we understand that. Now we want to think about what the tissue looks like. Where is this whole battle taking place? So this battle, once again, is taking place in the tissues. So let's take a look at, since we all have COVID on the mind, let's look at the lung tissues. So we've got the trachea that branches off into bronchi, and then those go into bronchioles, and it branches and branches, and the branches get smaller and smaller and smaller. Eventually you get these tiny little tubes that terminate in grape-like clusters that are essentially single cell thickness balloons. And that is where we do our gas exchange. And then when you look at the lung, all of that pink, fluffy, spongy tissue in the lung is actually alveolar sacs packed in, crammed in next to each other. And that's why the lung is sort of so spongy. So that whole innate immune system thing that we were talking about happening in the tissue is happening in these fragile alveolar sacs. So these are very, very thin, very, very delicate, and all this is happening there. All right? So if we zoom in a little bit and look at this under a microscope, this is what our lung tissue looks like on a microscope. If we just take a thin, thin, thin slice of it and put it on a microscope, this is what it looks like. So we've got a bronchi here, and we've got some blood vessels, and this is another sort of a different angle of a bronchi, sort of gotten cross-sectioned, or diagonal sectioned. And then all this lacy stuff here with all the open space in it, that's actually the alveolar tissue. Now if we zoom into that a little bit more, we'll see that we've got lung tissue here, and then we've got these fragile alveoli, and you can see they are one cell thick. And that thinness is what allows gas to actually pass between those cells into and out of the bloodstream. So our carbon dioxide comes out of the bloodstream into the alveoli to be breathed out, and oxygen comes in from outside world into the alveoli and is able to diffuse into the bloodstream. So it's pretty remarkable. Going back and looking at, this is kind of an easier thing for your brain to get around. We'll pretend the alveoli look like this. So when the earliest COVID-19 fatalities happened, when they looked at their lung tissue on autopsy, what they found was not that the alveoli were filled with fluid as you'd see in pneumonia. Instead, what they found was the inside of all of the bubbles had been lined with this very, very thick, gummy mucus that had consolidated, which then added this thick, impenetrable layer to the inside of the alveoli, and that was preventing gas exchange. That's why the respirators, the ventilators, don't help everyone, because forcing air in and out of the system isn't necessarily enough to get it through that thick mucus that had built up and lined the inside of the alveoli. Um, so that's one of the reasons. One of the reasons that steroids haven't been as much use in this is because, again, the problem's not that the lung tissue is swelling up and closing. And if that were the case, the steroids would help quite a bit. But instead, what we're getting is this lack of resolution in the tissue, and the steroids actually make that worse. So the steroids haven't necessarily made it worse for everybody, but they haven't been as useful as they traditionally are in fulminant cytokine cascades. So anyway, I just wanted to sort of mention that that's sort of what that was looking like, and that's what they were finding with COVID-19. So while we're talking about that, let's talk about phlegm for a second. So all of your mucous membranes, so the inside of your nose, the inside of your mouth, your throat, your GI tract, the inside of your bladder, and the inside of your lungs, those are all mucous membranes. And they're called mucous membranes because they have mucus on them. So mucus is supposed to be there. There should be a thin layer of mucus coating your mucous membranes. And the first reason is they keep those mucous membranes hydrated and moist. All right, so they keep them from drying out. The other purpose that our naturally occurring mucus serves is to give us a protective layer on those mucous membranes to protect us from pathogens just going straight into those fragile cells and straight into our body. So most of the time, so like pollens and things like that, they get stuck in the mucus, and then our body's able to sweep them away. We have these little cilia that push the mucus around. So normally we can push things back out when they get stuck in the mucus. Now sometimes we get such a large dose of a pathogen that it's able to overcome that system and it gets through the mucus. Some pathogens also have specific mechanisms where they hijack the biochemistry of the mucus, and it enables them to burrow through the mucus and get to our cells. What an interesting thing that I found is that different respiratory infections actually have different mechanisms to deal with our mucus layer. Now, once you get an infection in your mucous membranes, the mucous membranes respond by producing more mucus, trying to push that infection away and get it out. So that's one of the reasons we get more snot when we get a cold or a virus or allergies. So our body's making more mucus to push that stuff away from us. Now the pathogens themselves also trigger, they have different mechanisms for making more mucus. And then the innate immune response, that inflammatory process, our 4 superstar inflammatory cytokines, those also increase mucus production. So we have, what was that, 3 ways, maybe 4 ways? I kind of lost count. But we have several ways that infections make mucous membranes make more mucus. All right. And then what I wasn't able to find is what the biochemical Western mechanism is for why the mucus goes from thin to congealing and becoming very, very thick. One thing I did find was that the neutrophils that have been brought into the tissue to fight the infection also end up getting pushed out into the mucus. And when the more neutrophils there are in the mucus, the more thick and sticky the mucus gets. So it may be that the COVID-19, and this is purely speculation, this is not based on anything I've read, this might be completely wrong, so do not take this as gospel. But one of the things that made me wonder is if that really high level of innate immune response, bringing in all those neutrophils, was part of what was causing the mucus to congeal. So what's really interesting about that to me is that in Chinese medicine, we look at different symptoms and how an illness presents. And like the COVID-19 virus is presenting as dampness in the lungs, and then that dampness becomes damp heat, and then the heat becomes more and more toxic. And as the heat gets hotter, it burns up the fluid and damages the fluids and causes the fluids to congeal. So the Chinese have a really nice way of talking about this that matches the end result of what we're seeing, and also matches the symptoms. It doesn't give us the biochemical immunological mechanism, but I do think it's interesting that, one of the symptoms of inflammation is actual physical heat. So I kind of think there's a parallel between this innate immune response and the heat pathogen that they're talking about in Chinese medicine. So I thought that was a nice overlay. And so since I know a lot of my colleagues, I'm both a naturopathic doctor and an acupuncturist, so I have a lot of acupuncture colleagues. So I always like to point out when we get fun things like that. So I'm not sure that I fully laid out the whole cytokine storm thing. So before we go back to elderberry, we need to talk about that cytokine storm. So our 4 celebrity pro-inflammatory, pro-immune activating cytokines, when that danger signal gets louder and louder and louder, we will eventually can get bad enough. Now this is actually very rare. One of the reasons COVID is such a big deal is because a higher percentage of people that get sick actually develop this rare cytokine storm. And that basically means the cytokine levels have gotten so high that the call to kill overrides any possible resolving signal we can send, and then we start getting cell damage, and too many cells die, we get too much mucus, too much phlegm, we can't breathe. So that's what's called a fatal cytokine storm. All right, so I think I did explain that, but it's worth explaining again because that was sort of the point of the talk. So back to elderberry. So elderberry does increase our 4 celebrity pro-immune activating, pro-inflammatory cytokines: interleukin-1 beta, interleukin-6, interleukin-8, and most importantly, TNF-alpha. So these are the same cytokines that trigger the immune response in the first place, so that's good. These are also the same cytokines that are responsible for the cytokine storm, which can kill you, and that's bad. So based on that, what's our answer? Is elderberry good, or is it potentially dangerous? Well, my favorite answer to all of these kinds of questions is always the dreaded, it depends. So really with elderberry, it's an issue of scale. So elderberry extract increases those 4 cytokines. If a person takes a teaspoon of elderberry extract, those 4 cytokines will go up about 2 to 10 times their normal level. So that's a pretty big leap. Here's the thing, you may read that it increases those cytokines a whole lot more. And all of that, and all the internet rumors that elderberry extract would kill you if you got COVID-19, all of those are based on this one particular article. So in this one experiment, instead of giving healthy people a teaspoon of elderberry and checking their blood and counting their cytokines and their white blood cells and seeing what changed, instead what they did is they had 12 people, which is a very small number for an experiment. They drew their blood, and they then extracted only the monocytes out of their blood, and then they added the monocytes to a solution of a specific brand of elderberry syrup called sambucol. And then they measured how much TNF-alpha those monocytes secreted. And in that one experiment, those monocytes, when they were being drenched and physically soaked in sambucol, their secretion of TNF-alpha specifically increased more like to 45 times its normal level. So based on this, somebody in the media saw that one article and they made this huge leap that and then they also read that TNF-alpha was one of the things that caused the cytokine storm, and they made this huge leap and said, well, then elderberry is going to cause a cytokine storm and it's really dangerous and nobody should ever take it, and it should be taken off the market, which of course the pharmaceutical companies love to hear that. So that got spread around a little bit. Let's put that in perspective a couple of different ways. First, there are hundreds and hundreds of clinical studies using real human beings studying the effects of elderberry. And when you give elderberry to a human, it's going through their whole system. It's not going and wrapping itself around the monocytes. So soaking monocytes directly in Sambucus is a very unrealistic scenario that would never actually happen when you're taking a supplement. So first of all, that means that scenario can't be, you can't map what's going to happen in the actual body from that scenario. And incidentally, the article that I was telling you about, that study was actually designed to show how great elderberry was and how powerful it was. They never really dreamed that it would get flipped around and be used as a reason to never take elderberry because it was scary. Anyway, so the human studies really just show that elderberry has the potential to double or 10 times, or take the levels up 10 times their normal amount. So it's much smaller than that 45 times increase. So that's the first thing I wanted to clarify. And then the next thing we want to look at is what other things can increase those same cytokines. So for instance, running a marathon, which is very, very hard on your body, running a marathon can actually increase those cytokines up to 100 times their normal level. So that's way more than what elderberry does. And most people don't die from running marathons. Now here's the really final, really important piece of perspective. When someone's cytokine levels have to get up to 4,000 to 5,000 times their normal level before you approach the threshold where a cytokine storm actually begins, that could become fatal. So you've got a lot of bandwidth between bumping up your cytokine levels to 10 times their normal level versus 5,000 times their normal level. So when you put the scale perspective on it, there's no possible way that elderberry could trigger a cytokine storm on its own. If someone's mildly ill with COVID virus, there's no possible way that elderberry could possibly trigger them to spontaneously go into a cytokine storm. Now, theoretically, if someone who was just about to go into a cytokine storm, let's say their cytokine levels, they are so sick that their cytokine levels have gotten up to 3,995 times their normal levels, and for some reason they decide that what they really need to do is take a bunch of elderberry syrup and that's going to fix everything. Really, actually, they're going to be in the hospital at that point, but maybe that elderberry could be the final thing that tips them over, maybe. The reality is when your cytokine levels are that high, your fever is like 105 or 104, 105, you're not thinking, you're delirious, you're hallucinating, you're in the hospital, probably on IV medications and probably on a respirator at that point. So the idea of elderberry being a problem, by the time it would actually be a problem, the idea of it is essentially moot. All right. And that's basically what that says. So in a normal, healthy person, taking a teaspoon of elderberry extract, we actually have a lot of data that shows that it is actively helpful in getting just enough of your immune system ready to go and kind of looking around and waiting so that when the virus arrives, the immune system's already there to take it out. So we actually have evidence that that is true. And then if people do still get sick, taking a little bit of elderberry can give you a little bump up in that immune response so that your immune response is just a little bit stronger, and it can help shorten the length of a respiratory virus like a cold or a flu or something like COVID. And so for people that get just a mild version of COVID, elderberry could potentially still be helpful. All right, so closing thoughts on that. Now that I've just told you that elderberry is perfectly safe and you're welcome to take it, I do need to make a couple of points. One is that there's one big exception to that, and that is when people have active autoimmune disease. That bump up in TNF alpha can actually increase Th17 and Th22 cell lines. And if you'll remember from back when we were looking at the family tree, the Th17 were the T cells that did the tissue damage in autoimmune disease, and the Th22 cells were the ones that made your antibodies more aggressive. So if somebody has active autoimmune disease, you do not want to make their antibodies to self more aggressive. So there is a possibility that elderberry could make someone with autoimmune disease, it could make their autoimmune disease worse. I think this is primary theoretical. I don't believe there's any studies on this. One of my teachers that has a lot of experience treating autoimmune disease feels like that in retrospect, when he looks back at his old cases, he feels that in the cases where he gave elderberry extract to people with autoimmune disease, he thinks they had worse outcomes. So again, that's not a formal study. It's an impression of one of my teachers and his reflection looking at new data on how the specifics of how the cytokines work with elderberry. So another closing thought is that traditionally, the part of the elder plant that was used to fight viruses and respiratory infections was not actually the berry. Traditionally, it was actually the leaves and the flower. And the extract of the elder leaf and elder flower actually stimulate different cytokines, and they support slightly different angles for the immune approach. We don't have the same problem with it pushing the gas pedal on all 4 of the inflammatory cytokines. So the elder flower and elder leaf extract would be able to be used in people with autoimmune disease if you really wanted. And you'd also be able to safely use them even when the cytokines were getting fairly high. So I think that's pretty interesting. They're not as in common use now because the berry is delicious and it was really easy to extract, and it sort of saturated the market, and the companies tend to make what they think people are going to buy. So the elderflower and elder leaf, those are much harder to find, but that is actually the traditional form of medicine. And for those of you in Chinese medicine, that's really similar to the mulberry plant, where we have different parts of the mulberry plant being used for different systems and having very different actions. So that's sang shen, which is the mulberry fruit, sang ye, which is the mulberry leaf, and the sang bai pi, which is the mulberry twig or the mulberry bark. And you know, those are actually described in completely different systems of Chinese herbal medicine, but they're all actually the same plant. So this is the same kind of idea. And then the last thing that I want to leave you with is this really delightful idea that's called the doctrine of signatures. So the doctrine of signatures is this folk idea in herbalism that says that plants will show you in some way what they're good for treating. And it may be that the plant looks like the organ that it treats, or it might have a taste, or, you know, if you're treating respiratory things, a lot of the things that treat respiratory infections and respiratory issues are very aromatic, and they have these expansive smells. Some plants that are really good for increasing energy have these really strong spines to them and things like that. So this is called the doctrine of signatures, and I've always kind of loved it. And you have to apply a fair amount of artistic interpretation a lot of times to make the doctrine of signatures match up, but it's still a lovely idea. And so with that idea, we're going to think about the branching in the lungs ending in round grape-like clusters, and then we're going to look at this beautiful branching pattern on the elderberry and see that the branching of the elderberry flowers and fruits actually is almost exactly the same shape and angle as the branching of the lung system. So I just think that's a lovely little overlay. So that's it. That's my explanation of the cytokine storm. You just got a crash course in functional immunology, and this is my opinion about why I just don't think that the idea that elderberry syrup can cause a fatal cytokine storm, I just feel like that has no merit at all. All right, well, I hope you found this helpful and enjoyable, and look forward to seeing you and on another installment, and hope you tune in to the next class. Take care. Bye-bye.